March, then on 12th of March the second will be out, but you submit it after the end of the Easter break, 21st of April. Also yet, before the break, the third assignment will go out with a submission also after, but 1 week later on 28th of April. So actually these two assignments you'll have long time to solve. Each one of them has 1 week before the break, 1 week after the break. So if you organize yourself well enough, you can have the break clean off with that. Because basically you won't need 2 weeks to solve the assignment. A few hours if you're concentrated. And the last one as it was before with I think 12. So it's updated there, and expect the first one to be released on Thursday, but I will send it. And we move on to the nucleolus. So first we will see some natural way to compare two different imputations. In imputations, it's a payoff vector which is feasible in terms that it does divide the total value of the grant collision, and it is individually rational, so that the payoff to each of the agents is non-negative, right? So we will define some way to compare different imputations, and then based on them, on this comparison, we will define the solution concept of nucleolus as the payoff vector which is the best given that way of comparing the vectors of payoffs. Okay, and then we will look at different properties of the nucleolus, and you will see why this is indeed an important. So let's first of all recall we did define the excess of the coalition before, but I'll have to remind it now. So in excess of the coalition, so if we have a cooperative game with the set of agents A and the characteristic function V, then let X be a payoff distribution. And let C be coalition. Then the excess. We will denote it as P of C under the payoff distribution. X is just the difference between the value of that coalition and the total payoff that the members of the coalition get, right? So this is the sum of the payoffs to the members of the coalition. So what does this value mean? If it is negative, then the members of the coalitions are happy or unhappy? That's how much they can do on their own. That's how much they are paid given this payoff distribution. So if this difference is negative, they are happy or not? Happy, right? That means that currently they're getting more than they could do on their own, right, without arrondissement. So negative excess is good. Positive excess is bad. And in fact, we can define the value, the notion of the core in terms of excess. How? So the core of the game, and V would be all payoff vectors, so that X is an imputation that is efficient and individually rational. each coalition C, X defines a non-positive excess. Right? Then that coalition would not be able to make more than it's currently given by X, which is exactly the definition of the pool. So that's exactly the same definition. So that's an excess, and what we want to do, we want to minimize the excess for all the coalitions. Right? That would be a good solution to have. So if I have, for instance, 3 agents, 1, 2, 3, and I give them, and the value of coalition of the first one and the second one is say 8, and the payoff that I give them is 3, 2, 5, then the excess of coalition 1, 2 under X is 8 minus 3 plus 2, 3. So these guys are not happy in this case. Right? This would not be a payoff in the pool. So excess, in fact, is just the measure of the dissatisfaction of a coalition, how much they want to complain. So now, let me just extend this example to just define, so we have 3 agents again, and we would define the values. Let each singleton get a 0, and the pairs would get, we could leave this one, 1 and 2 would get 5, 1 and 3, as well as 2 and 3 would get 6, and the ground coalition would get 8. And let me compare now two payoff vectors. X is 3, 3, 2, and Y, which is 2, 3, 3. Which one would be better? So first, well, let's compute the excesses for each coalition under these two vectors. So that would be for each coalition of the agents. I'm going to compute the excess of this coalition here. Okay. So we have the singletons, and we have the pairs. Now note that for always actually the empty coalition and the ground coalition, if I am given imputation vectors, I can always exclude those because their excesses under any imputation X would be 0. Why is that? Because if X is an imputation, then it distributes the value of the ground coalition exactly, so the difference must be 0, right? And for the empty coalition, its value is 0, and the members of that coalition get 0 under any pair vector, so that's 0 as well, 0. Right? So for the ground coalition and for the empty coalition, these are 0, so we can ignore them. Okay, so agent number 1, his value is 0. He gets 3 under the pair vector X, so his success is 0 minus 3 minus 3. And it will be minus 2 here. Similarly, we get minus 3 minus 2 minus 3 minus 3. Right? For the pairs, the total payoff of these guys is 6, and their value is 5, so the excess is minus 1. 1 and 3 together get 5, their value is 5, so that's 0. And 2 and 3, the value, sorry, yeah, that was 6. Correct. So that would be 1. And same for 2 and 3, right? The value is 6, and what they're getting under the vector x is 5, so it's really 1. Here we get 1, 0, 0. Now, okay, we have now the sequence of excesses for all collisions. One natural way to compare them, so we can look at them as vectors, right? And we can compare them lexicographically, in fact. So, and that's exactly the idea. But first of all, I will have to reorder them in the decreasing order of the excesses. So we reorder the excess vectors, what we call them, excess under x and excess under y in the so we get e of x, and we denote it by bar, right? So that will be reordered vector excesses for x. We will have 1, 1, minus 1. Actually, let's just opposite all of those. 1, 1, minus 1, minus 2, minus 3, minus 3. And that of y gives us 1, 0, 0, and the same. And we can compare them lexicographically, so let's denote by, I don't know, say this. Lexicographic ordering of vectors in Rn. Which means that for any two vectors x and y, I would say that x is lexicographically larger than y, if and only if either x actually is equal to y, or there exists some entry t such that for every entry I before t, we have that the entries of x and y are equal, and at t, xi becomes strictly greater than yi. So that might be t. So in our case, the first entry is the same, and in the second entry we see that x is larger than y, so we don't need to check the rest of the vectors, and we would say that then x is better than y as a Bayes vector, given that that's the way that we are going to compare them by lexicographic order of their excesses. Any questions up to now? So the nucleolus rules of the game. And V would be the set of what we call the new clause. So that would be all the imputations. I be the set of imputations. So that for every imputation y, we have that x is better than y, that is the ordered vector of excesses under y is larger than the ordered vector of excesses under x, right? We want to minimize excess. Oh, yeah, that's wrong. Y is better than x, because the excess of x was larger. So this is a set of solutions. And now we will see how it looks like, but let's do an example before. Do I need that anymore? We have a little firm that went bankrupt, and it is now in debt to 3 of its creditors. And there is it owes £10,000 to creditor A, 20,000 to creditor B, and 30,000 to creditor C. Now it's only left with £36,000 to pay its debts. So the question is, how should the firm divide the money among the creditors so that they do not complain? So yeah, the budget is, you would say they would always complain, but we are talking about credible complaints. So how to divide this? What's the naive solution? Naive, simple.
6,000, 12,000, and 19,000?
Proportionally,
Yeah.
right? So one of the solutions is, indeed, we can divide the money proportionally to the amount of debt to that creditor. That's one option. So let's call it X, and yeah, I will ignore the thousands. So that would be indeed 6, 12, and 80, the proportional. Well, let's try to see what the nucleolus would suggest, and maybe let's try to see what Shapley value would suggest. So we know now different concepts that we may like to apply. And so to compute the nucleolus and the Shapley value as well, we need to compute the coalitional values. Okay, so the agents now would be the creditors, and the possible coalitions would be different subsets that they can form. So what would be the values of those coalitions? So the empty coalition would expect to get a payment of 0. The coalition of all three can together get the whole budget, so 36, right? And let's see what happens for the others. What would be the value of a coalition of a single creditor A? So if you look at the amount of debt for B and C, there would be 50,000, which is more than the budget of the bankrupt firm. B and C can get the whole budget for them, right? And A can't expect anything. So his value on his own would be 0, right? A is not guaranteed any payment as B and C can exhaust the budget. Same for B, right? A and C together have 40,000 pounds, so it eats the whole budget. So creditor B also can hope for nothing, while for C it's already not the case, because A and B together would only take 30,000, and then there are 6,000 left, and he is guaranteed this payment on his own without cooperating with other creditors. In a similar way, A and B together can hope to get 6,000, because 30 may go to C on his own. A and C as a coalition can guarantee to themselves 16, that this is what's left after paying to 20,000 to B. And for BC, we have 26. So we got the characteristic function. So, how do I look for an imputation which is pure? So let us have an imputation X, specifying the payoffs for the three creditors, A, B, C. So that means that the sum of those payments must be 36, right? And each of them is also not. So we want to find the lexicographically smallest vector among all those vectors that look like this. So first of all, we will try to minimize the largest possible excess. After that is done, then we will try to minimize the second largest possible excess, and so on. That's how we compute the nucleolus. So let's do it gradually. So let me call it the coalition S of the agents. That would be its value. That would be the excess of X, of S, sorry, under X. And we will make a space for writing for 4 different pair vectors over there. determine the proportional one, 6, 12, 18. So we have solution A, B, C, B, C, B, C. Again, I'm ignoring the empty collision and the large and the grand collision because their excesses are 0. I know that. Right, and here we have 0, 0, 6, 6, 16, 26. Now the excess of A would be 0 minus x1, the excess of B is 0 minus x2, the excess of C is 6 minus x3, AB 6 minus x1 minus x2, AC 16 minus x1 minus x3, and BC 26 minus x2 minus x3. And for this vector, we'll get minus 6, minus 12, minus 12, minus 12 again, minus 8, and minus 4. So now we are trying to see if there is something to do, if there is a way to rearrange the payment for the agent so that we somehow improve on the maximal excess. The maximal excess here is for the collision B and C. It's minus 4. Right. So, is there a way to make them happier? That is increasing x2 and x3 somehow, right? So that the excess goes down a little bit. Now, if I increase x2 and x3 at the same time and by the same rate, actually I decrease the payments to creditor A, so the excess of collision of the singleton collision of that creditor would go down, right? So would go up, sorry. So how much I can afford. So this one is minus 4 now, this one is minus 6. I want to, once again, I want to increase the largest, to decrease the largest excess. When I'm increasing the payments for x2 and x3, at the same rate, I decrease the payment to x1, so this goes down, this goes up. And they would meet at minus 5. So the best thing I can do actually is to pay agent 1, agent A, 5, and increase by 1 x1 or x2. Let's just remove x2. Let's just, for instance, increase x3 and see what happens. So now we will have minus 5 here and minus 5 here. And for the rest, so it stays minus 12 here. Here it goes down by 1. For AB, it goes up by 1 because the payment of B didn't change. The payment of A has decreased. And here it stays the same. So that's the vector of excesses for this vector. Now this is already better. This is already an improvement on this vector, right? Because the first coordinate will be lower. Now, can we do better than that? Now, with the largest excess, that's nothing to do. The largest excess now in these two entries. And if we put this down, this one grows. If we put this one down, that one grows. So nothing to do. So the largest excess, we have to stay with minus 5. So we now look at the next one. And that's to the coalition of A and C. So now I'm looking to improve on the payment of these two guys so that the excess goes down. But pay attention that, so these two guys are agent A and agent C, but x1 I cannot touch, right, because of the balance in the largest possible excess. So x1 is fixed to 5 now, so the only payment that I can improve on is the payment to the third agent. Okay. And now the question, how much I can move that. So I can increase the payment to agent 3. This will affect the values of the other coalitions. Right? This will affect the value of the complement coalition B. So when the payment to agent 3 goes down, the payment to agent 2 will go the other way around. The payment to agent 3 goes up, this goes down, so the excess of this coalition will increase. Now they are -8 against -12, so somehow we are going to meet them. And also it affects the value of the coalition AB. Right? So by changing the payoff of vector of agent 3, we affect the payoffs of the second agent. The first one we don't touch, and these are this coalition, so we have to look at this excess, and this is coalition at AB, so we have to look at this excess. Now the closest to the largest excess -A is this one, so that's the one that we have to focus now, right, and meet these two, so the middle point will be 9.5. And this means that we are increasing the payoff of agent 3 by 1.5, making it 5, 20.5. What is left to the second agent, it goes down by 1.5, so it's 10.5. And if we compare all the excesses, there will be -5, no change here. This one will increase by 1.5, the payment of agent B. This one will decrease by 1.5, the payment of agent C. Increase here by the same amount, decrease here by the same amount. These two guys meet now, they are the same. And this one as before. And that is the nucleolus, because the largest possible excess, excess does not leave me the option to touch this number. The second one does not allow me to touch this number, and that fixes the third one. So there's nothing else to do. So that's our nucleolus distribution. Let's compare it to the Shapley value. I'll tell you why. Say, I would leave the computation to you, you know how to do that, but the Shapley value of this game is 6, 11, and 19. So not quite the same as nucleolus, but not far from it. And it gives us excesses of -6, -11, -13, -11, -9, and -4. Why it's interesting to compare nucleolus to Shapley value, this is because of its properties. And the properties are as follows. First of all, I'm going to always exist. Moreover, it is unique. And this is great. That's a solution which is not a set, which is a particular pair of vectors. But not just a pair of vector. It also it is efficient. Individually rational, but that's actually every imputation. But also it satisfies the symmetry and the dummy axioms. Do you remember what are those? We defined them when we looked at the Shapley value. The symmetry axiom says if we have two agents, I and j, that contribute with marginal contribution to each coalition is the same, their payoff must be the same. That's symmetry. So nucleolus satisfies that. Dummy means if I have an agent that does not contribute anything to any coalition at all, his payoff must be 0, and nucleolus satisfies that as well. Now, it's efficient, symmetric, and satisfies the dummy axiom. These are 3 axioms of the Shapley value. The Shapley value has also the 4th axiom, and if you remember, we said that Shapley value is the only pair of distribution that satisfies all 4 axioms. Meaning, if nucleolus, which is different as you see in this example from the Shapley value, satisfies 3 of the axioms, it must violate the 4th axiom. So it is not additive. However, as opposed to the Shapley value, who is not always stable, if the core of the game is not empty, then nucleolus would be a member in the core. So if the core is not empty, then nucleolus is so it is a pretty nice solution. It's unique, it always does exist. If the core is not empty, then it's also a stable solution, and also it is pretty fair, in fact, right? So it's symmetric and it satisfies the dynamics. The only issue with it could be that computing it is not always a paradise. So let me comment on that a little bit. So generally, computing it is a little harder than computing the Shapley value. And that's because what we have to do, we have to optimize first for the largest success. Then, when that's done, then we have to optimize for the second largest excess, and so on. That brings us basically to solving optimization problem recursively, right? Many optimization problems. Each of them would be a linear one, but there will be a recursive definition. So to define that formally, let us recall a little bit the mathematical problems for the epsilon core and the least core. Right? So the epsilon core is is the set of all the distributions. If the total payoff received by each coalition is no less than the value of that coalition minus epsilon. So epsilon basically here defines the excess of the coalition, right? That's exactly the difference between the value of the coalition and the payoff that the members of the coalition get together, and that's for every coalition. And then we said that we of course say if we define, if we take epsilon large enough, then of course we can satisfy all those constraints for all the coalitions. So the point is of course to find the minimum value. Let's call it epsilon star, and that's just the infimum of all of those, so that the epsilon core is non-negative. And then we said that the least core of the game is this epsilon star. And we can find it by solving a linear program, right? So we want to minimize this value of excess so that the core, the epsilon core, is non-empty. So we have the imputation, each one gets a non-negative payoff, the sum of payoffs is exactly the value of the ground coalition, and for each coalition of players we get that their total payment is greater or equal than the value minus excess, minus epsilon. That's for the least core. Now for the nucleolus, we will have to do to solve a similar program, but recursively for each, for the largest possible excess, but then the second largest, and so on. So, into a look. So the nucleolus is a solution to problems that we call them optimization problems, O1 and so on, OK, actually ON. So it's exactly as the number of agents, which are defined possibly as follows. Well, let's define the first one. So we want to minimize the largest possible excess, we call it epsilon, so that the amount of payoffs for each coalition are greater or equal than the value minus the excess. And that's now for each coalition. So that would be the first. And then the next program would be to minimize epsilon, where the set of constraints would be given by all the previous optimization problems that we had on the way. So the sum of the agent payoffs for each coalition would be greater or equal then the value of that collision minus epsilon 0, then there would be epsilon 1, and so on. Epsilon j minus 1. And finally, epsilon, which is the same variable that I'm minimizing here. So that's actually the decision variable for the current problem. And those guys are solutions, the values, the objective values for the previous problems. But let me tell you first for which coalitions C we have those constraints. So here we had our first constraint for all the coalitions. Here we will have it for all the coalitions in some set of coalitions S1. I will give you the definition of this set, but that would depend on the previous problems that we solved. In this case, just the first one. And then for the following cases, it would be the set. We take the set of coalitions at the previous step and exclude from that all the coalitions in the step before. And at the last step, it would be all those at j minus. So that defines the problem at step j. Now I have to tell you who are these guys and who are these guys. So epsilon j minus phi is the optimal objective value for the problem at step j minus 1. So that's the solution of the problem in the previous step. The first step does not depend on anything happening before it, right? So the second one, we can rely on the previous step. And the Sj minus 1 is the set of coalitions, so it's a collection of coalitions. The members here are coalitions. For which the constraints that we had here in the corresponding step realized as equalities. So these are tight constraints, meaning that those collisions we cannot touch anymore. Otherwise, we will spoil the value of excess that we achieved in the previous step. So we exclude those coalitions and only look at those we are remaining. The constraints are realized properties given the optimal solution. Problem. Step changes. So it is still a sequence of just linear equations, looking very similar to this one, but that's many of them, and the definition is recursive, which is not always the best thing to do. Let's have a break.